Let's do a fun little exercise where we play around with some concepts that we've introduced recently and apply them to the second form of Bloch's theorem in 3 dimensions. So when we first were talking about this, we said that it's rather easy if you just focus on a very specific lattice vector R, that you can write down that it's possible that there are solutions which take the following form, namely the products of a plane wave, right, exponential kr, times a function u of r, which is periodic with the same periodicity r that we were talking about here. Okay, and then we said at that time, if you just focus on a single lattice vector r, that's fine. But what we would really like to show is that it's possible that there are solutions of this particular form, where this function u of r is periodic not just for a single lattice vector r, but actually for all of the lattice vectors that there are in the 3-dimensional lattice. So this is what we're doing here. And we're going to describe our lattice by the primitive lattice vectors and also the primitive reciprocal lattice vectors. So every lattice vector R can be written as a linear combination of these 3 guys, A1, A2, and A3. But we also know that every reciprocal lattice vector can be written as a linear combination of 3 other guys, B1, B2, and B3. Okay. So if we have discrete translation symmetry, aka periodicity in 3 dimensions, that means that the operator theta that describes Maxwell equations will actually commute with all 3 translation operators over A1, A2, and A3. So let's write that as such. So this thing is equal to 0 for all directions. And that means we know that it's possible to find a certain function, an eigensolution H, which not only is an eigensolution of the theta operator of Maxwell's equations, but which also satisfies the eigenproblems that are set up by the different translation operators. So all of these 3 operators, 4 operators actually, they have common eigenfunctions. So that means that if you look at the translation operator and we translate, for example, over AI, so if you have R plus AI over here, because we're dealing with eigenproblems, we end up with the same H of R, but we multiply this with a certain eigenvalue lambda. Now this eigenvalue, we could call it lambda or mu or George or whatever, but let's here call it exponential 2 pi j theta I. So that's just a convention to make our life a bit easier. Basically what we're doing is we're introducing a number theta, which is not the eigenvalue itself, but rather proportional to the logarithm of the eigenvalue. Okay, so we have 3 different theta values. Now, just for fun, let's construct a k-vector, which is defined as the following linear combination. It's defined as theta 1 times b1 plus theta 2 b2 plus theta 3 b3. So there's nothing that forbids me to define a certain k-vector like this. There's also nothing that forbids me from defining a certain function u of r, which is then given by exponential minus the same k-vector that we've just defined, r, times the eigenfunction that we're dealing with, h of r. So again, that's just the definition. There's nothing that forbids me from doing this. Obviously, all of this will look very familiar to you. It's basically just the same type of setup that we had when we were talking about Bloch's theorem, a second form of it in just 1 dimension. The only thing that we need to do now, just to complete the proof in multiple dimensions, is showing that this function u of r that we've defined, that this thing is actually periodic for all possible translations that we have. So we need to have that r plus aj, if we plug that into u, that we get back the same u of r, not just for 1 translation in 1 direction, but actually for translations in all 3 independent directions. So this was the rather long setup for the exercise. Now comes the exercise proper, which is just pausing the video and see if you use all of these definitions, can you really show that this function u of r is periodic in all three directions. Good luck. Okay, so let's just plug in everything we know. So just first, let's look at the definition. U of r plus aj. So if we look at how we've defined our function u up there, then we just replace r by r plus aj. So we have this first vector exponential minus j k r, and then we have exponential minus j k then aj. Okay, like this. And then finally we have h of r, where we also should replace r by r plus aj. Okay. Let's continue expanding this. First we have our boring factor here, kr, and then we have exponential minus j, and then the scalar product of k with aj. Now k is just not any vector, we've actually defined this over here, so we can substitute this expression for k in our equations over here. So this becomes theta 1 b1 theta 2 b2 theta 3 b3, and then we have scalar product aj. Okay, and then if you look at the third term we had here, h of r plus aj, well, because we have that this h is also an eigenfunction of that operator here, we just can copy and paste this thing over there, replacing I with j, just to say that h of r plus aj then becomes exponential 2 pi j theta j times h of r. Okay. We're getting very close to where we need to be. Exponential minus j kr. Okay. And then we have here in our exponential all sorts of products between lattice vectors and reciprocal lattice vectors. And we know that if the indices of the a's and the b's will be different, then this thing will become 0. And if they're the same, then we actually end up with 2 pi. So the only term that's left here will be a term with index j. So we will have theta j times 2 pi. Okay. And then the good news is, so if we then copy and paste this thing again, 2 pi j theta j h of r. Okay. Then now we can say that this guy cancels with that guy. And then we just have exponential minus j k of r, h of r. And if we look back at our definition of our function u up there, then we see that we have exactly recovered that definition up here. So showing that our function is indeed periodic for all possible directions, for all three directions that we have. So this completes the proof of the second form of Bloch's theorem.